Okay, so hello everyone. Welcome to episode 40 of Warsaw Quantum Computing Group Meetups. And today we have a pleasure to host Dr. Özlem Salehi. Özlem is from Turkey, but she's also collaborating with Polish Academy of Sciences. So I believe that Özlem will also give a brief introduction. And the title of the lecture today is Unconstrained Binary Models of the Traveling Salesman Problem Variants for Quantum Optimization. So as usually, this lecture is recorded, so hopefully the video will be later available on our YouTube channel. If you have any questions during the lecture, please post your questions on our chat. So at the end, there will be Q&A session, so we can ask questions. But if you have very important, urgent questions related to specific slides, then also feel free to interrupt, so we can just make this this lecture more interactive. Before we start, I would like to thank our strategic partners, Narto and Cogit, for supporting us, and our honorary partners for helping us in organizing, promoting this event. And I think that now we can start the lecture. So I will stop sharing my slides, and Özlem, if you are ready, the Zoom is yours. So thank you once again for accepting our invitation, and we can start.
Thank you for the introduction, and thanks for the invitation. Let me share my screen. Okay, so as Pavel mentioned, if you don't understand something, just feel free to interrupt, type in chat. I will be happy to answer the questions. So today I will present our work titled Unconstrained Binary Models of the Traveling Salesman Problem Variants for Quantum Optimization. This is a joint work with Adam Gloss and Yaroslav Mishak. Currently, I am working as a postdoctoral researcher at Polish Academy of Sciences, Institute of Theoretical and Applied Informatics in Gliwice. I am also affiliated with Cuba. I am one of the coordinators of the education department. Here is a brief outline of the talk. First, I will talk about traveling salesman problem. Then I will explain what Cuba formulation is. And then I will talk about quantum annealing. Then we will move on to the actual problem, which is traveling salesman problem with time windows. Then I will briefly mention some experimental results. I think most of you have heard about traveling salesman problem. You are given a list of cities and you have the cost between the traveling each city. And your goal is to find a closed route so that you move between the cities, passing each city exactly once. And you want to find the route which has the minimum cost. So it is a minimization problem. You would like to minimize some cost function, but this is also subject to some constraint that you should visit each city exactly once. I can give you another example here, a more concrete example. Here you see like graph. So you are given this graph. It has 4 nodes labeled by 0, 1, 2, and 3. And between each, on each edge, you have a cost associated. For instance, this one is 1, this one is 1, but the cost of this edge is 3. So if you move through this edge, the cost is 3. And on the right-hand side, you see some routes and their associated costs. So for instance, in this one, right now, those numbers in red, they are denoting the order. So we start from, first we traverse this edge with cost 1, sorry, with cost 2. Then this one with cost 1. So let me start from scratch. Okay. First we visit this one, it has cost 2. Then we visit this edge, it has cost 1. Then we move through this edge, it has cost 1. And then we move through this edge, it has cost 1. So this means that the overall cost of this tour I just made is equal to 5. And here you also see this one as, so this is just a symmetric case. I start from this way. But for instance, if you check this one, on the bottom, where you like move like this. So we move here, here, and here, and this has cost 7. So our goal is to find the root with the minimum cost. In our case, it will be this one or this one. Only the order is like switched. But in general, you cannot just list all possible roots because this is really something infeasible. Listing there are n factorial roots, and you cannot just calculate the cost of each one and try to pick the one with the smallest cost. And indeed, this problem is known to be NP hard, meaning that we don't know any efficient classical algorithm for solving this problem. And quantum computing is offering some new approaches for solving optimization problems. And one of those techniques is quantum annealing. So it is a method for solving optimization problems, and TSP also falls into this category. And briefly, what is quantum annealing? So first of all, it runs not on the gate-based model. So maybe you are familiar with the gate-based model of IBM and many other companies, but this is running on adiabatic quantum framework. It's analog computation, unlike the gate-based model, where you apply sequentially some gates. Here, you apply some magnetic field to the qubits to perform computation. In quantum annealing, you have some qubits, and the adiabatic, let's say they are in their lowest energy state. Which is also called the ground state. And quantum adiabatic theorem guarantees that if the state of the system is evolved slowly enough, then it will always stay in the lowest energy solution, lowest energy state, in the ground state. And we are using this principle to optimize some function to find its lowest energy state. So first of all, we have an initial Hamiltonian. Here it's denoted by HI. So the system starts in the ground state of this initial Hamiltonian. And it's important that this initial Hamiltonian has some easy to prepare ground state. And then we have the problem Hamiltonian. And this problem Hamiltonian needs to encode your problem. I will explain what this means. And you may wonder what this A of S and B of S are. S here is the time. And at time 0, we have AS only. And if you check the graph on the right-hand side, B of S is 0. And this is called the annealing schedule. As time goes by, the impact of initial Hamiltonian is decreased, while the impact of problem Hamiltonian is increased through this A of S and B of S parameter. Because at the end, this A of S reaches 0, while this B of S is growing. So the system is evolved slowly. Initially, it starts, so quantum annealing right now is available through D-Wave machines. This D-Wave company, they have those quantum devices called quantum annealers. And the system is initially prepared in the equal superposition of all states, which is described by this initial Hamiltonian, where you are applying just X gates to all qubits. So you end up like in an equal superposition state. And then the system is driven by this problem Hamiltonian. And this problem Hamiltonian will encode our problem of interest, so that starting in the initial ground state and evolving the state slowly enough, we again end up with the ground state of this problem Hamiltonian. And here what we need to decide are those HI and JIJs. So this HI is called the bias, and JIJ, those are called the coupling constants. And here it's coupling two different qubits because it's applied, so this Pauly-Z operator is applied on spin I and spin J. And that corresponds to the following Ising model. It had the lowest energy state of the Ising model corresponds to the ground state of this problem Hamiltonian. So with this correspondence, if we can express our problem in the form of an Ising model so that we can determine HI and JIJ, then based on this, we know what magnetic field to apply on the qubits, and hence we can use quantum annealing to minimize the energy of this Ising model. So this expression here is the energy of the Ising model. And this is what we are trying to minimize. And those SI and SJs, they're -1 and 1. And in the end of the annealing process, we end up with an assignment to the spins. So they are either set to -1 or 1, so that we have the lowest energy. So we are looking for which SI should be set to 1, which SI should be set to -1, so that this function is minimized. And quantum annealing is doing this thanks to the quantum adiabatic theorem. This is a picture visual from D-Wave. So this is visualization for a single qubit. As a result of applying the external magnetic field, it has higher probability of ending up in state 1 or ending up in state 0. So we change this through the application of this external magnetic field that encodes our problem. So I mentioned that we need to express our problem like this in the form of an Ising model, so that minimizing our problem is equivalent to minimizing this Ising model. But often it is not very convenient to work with spin variables, -1 and 1, but it is easier to work with binary variables. And this leads us to the quadratic unconstrained binary optimization. So first I will discuss what quadratic unconstrained binary optimization is. And there is a really simple correspondence between this QUBO. In short, this is called a QUBO. And there is a very simple correspondence between QUBO and the Ising model. So what is a QUBO? Here, it's a minimization function, actually. And what you see here is a QUBO. So we have quadratic, and quadratic means that you should have terms of at most 2. For instance, x1, x2, or x1, xn. But you cannot have a term like x1, x2, x3. It's not possible because it's quadratic. And secondly, it is unconstrained, so it's not like minimize this subject to some constraints. You don't have any constraints, therefore it is unconstrained. It's binary, meaning that those xi's, they are binary variables. So they are either zeros or ones. And in compact form, you can express this using a vector matrix representation. Here where x's are, this x is the vector of binary variables, and this q is just a matrix containing all the constant terms like q11, q12. And the goal is to find xi's, meaning that which xi should be 0 and which xi should be 1. You are looking for this vector x such that this function is minimized. And once you can write your problem in this format, then you can convert it into an Ising model really simply, because they have almost the same form, except that this has binary variables, but in the Ising model, we had spin variables. But there's even more, because when you are thinking about some problem, most of the time you are thinking about something to optimize and some constraints. Think about TSP again. In TSP, we need to minimize an objective function, but we also have some constraint. And what is this constraint? It is that we need to have a closed route which passes through each t exactly once. And in classical optimization, actually, there are some models to define such problems. And one of those is integer linear program. And what is an integer linear program? In an integer linear program, you have first of all integer variables, and you want to minimize an objective function which is linear. and it is subject to some linear constraints, and they can be either equality or inequality constraints. In the case your objective is quadratic, it is called an integer quadratic program, and this is what ILP and IQP stand for here. And once you can formulate your program in this format, then you can always obtain an equivalent Cuba formulation. So this is also possible. So therefore, say you want to solve your problem using quantum annealing, you can first come up with an integer linear program, or maybe it already exists. And then you can come up with the Cuba, and then you can convert it to the Isaac model. What are the steps for the conversion? Let's go through this briefly to make it more concrete. First of all, we convert any inequality constraint into an equality constraint. And this is done through the slack variable. Here on the first line, we have an inequality constraint. And on the second line, we have the equivalence constraint where we have an equality sign here. And we use a slack variable. This is an integer variable so that it accommodates the difference. So if this is less than or equal to 10, let's say this is both x1 and x2, let's say they are 1, and this is 5, then the slack variable will take the value 5. So you should determine its range appropriately. Next thing you need to do is converting integer variables into binary variables, because in Cuba you have only binary variables. And this is also possible by introducing some new variables. So how do you do this? You need logarithmically many more variables for each integer variable. You use more than one variable to represent a single integer variable. And this is also possible. Next thing you do is you shouldn't have constraints in Cuba. And we use something called penalty method. So actually this is important. So what is this penalty method? Let's say we have a constraint saying that x1 plus x2 plus x3 should be equal to 1. But okay, we cannot have any constraint. We can only have an objective function. What we do is check this term, x1 plus x2 plus x3 minus 1 squared. This p is just a constant number. Let's say this is 5 for now. And we take this, let's say f of x is what we want to minimize. It is some function. And we add this term to this f of x. And now let's think what it does. Say x1 plus x2 plus x3 is really equal to 1. Then this will be 0. It will not have any impact on the objective. But let's say x1 plus x2 plus x3. Let's say this is equal to 3. In this case, 3 minus 1 is 2, and 2 squared is 4, and penalty term was 5. Then it will add an extra 20 here. But remember, our goal is to minimize this objective function. Therefore, this will not be a desired solution. So any violation of the constraint will end up as a penalty in the objective function. So this is how the penalty method works. An important thing is setting up that p-value, because if you set it too low, then it will not be too important when optimizing the function. You may violate some constraint in favor of minimizing this f of x. If you set it too high, then you will stop optimizing this f of x, but you will just try to enforce the constraints. So this is somewhat hard if your problem is complicated, how to set those p-values. But overall, this is what you do for each one of the constraints. And you need the square because you might have minus. This is actually why you need the square here, because in case all of them are set to 0, and let's say this is 0, if you don't have the square, you would have -1, and you will decrease the energy, and you don't want that. So this is why we have the square here. And finally, after doing this, you end up with Cuba formulation. And that's all. Overall, the thing is, if you define your problem through some constraints and some objective function, even if they are defined for integers, you can end up with a Cuba formulation. So to solve a problem, first express your problem as a Cuba formulation. Then you can obtain the equivalent Ising model through this mapping. It's you just replace all x's with spin variables, and you obtain the equivalent Ising model. And finally, you can use right now quantum annealing to find a variable assignment that minimizes the energy. So at the end of the annealing process, as I mentioned earlier, we will end up with some variable assignment saying, okay, x1 is 1, x2 is 0, x3 is 1, and so on. And this will have some meaning for us. And from this, we will come up with our solution to the problem. Now, let's talk about Cuba formulation for TSP. How to express this problem as a Cuba. This is how we will define our binary variables. We have xvi's such that this binary variable is equal to 1 if node v is visited at ith step in the tour and 0 otherwise. So this will be the meaning of xvi. And you see that we will have n square variables if you have n cities, because we will have x11, x12, x13, x1, and xn1, xn2, and so on. And when creating or coming up with a Cuba formulation, something you would like to desire is to have as minimum as possible number of variables. Why? Because the current quantum annealers, they are not really large. So to be able to solve some real instance, you should, the less number of variables you use, it is better. And there is this embedding problem, which I will discuss later on. So this is something you desire, to find a formulation which uses less number of variables, because it also increases the chances of error. And then using those variables, we will express our constraints. So we will like to have that each city V is visited exactly once. And what does this correspond to? So here, this constraint is saying that, so if you fix a V, if you fix some vertex, and if you take a sum over all I, meaning that you are taking the sum over the steps, then this should be exactly 1. So each city should be visited exactly once. This is what this constraint is saying. Let's give an example. Let's say there are only 3 cities for simplicity. And let's say I'm considering city 1. So there are 3 time points. And I am saying x11 plus x12 plus x13 should be equal to 1. So I should visit city 1 either at time 1, either at time 2, or either at time 3. So this is my first constraint. And my next constraint is that at time I, exactly one city is visited. I don't want a variable assignment in which I am visiting more than one city at a fixed I. And this is really similar if you check the form, but this time we have a fixed I and we are going through V's. And this looks like following. Let's say for I equals 2, this is saying x12 plus x22 plus x32 is equal to 1. So at time 2, you either visit city 1, city 2, or city 3. And exactly one city. No, not 0 or not more than 1. And overall, those 2 constraints will make sure that we will have a closed route which visits each city exactly once. So in the solution, for instance, we are expecting that, I don't know, maybe this is set to 1. Let's say we first visit city 1 we visit city 1 at time 3. Let's say those are times and those are cities. So we have 1, 2, and 3. Let's say at time 3 we are visiting city 1, and at time 2 we are visiting city 3, and initially we visit city 2. This might be a possible solution. And this would correspond to the following variable assignment. We will have x21 is set to 1, x32 is set to 1, x13 is set to 1, and all the remaining variables will be set to 0. So if we end up with such a solution, then we will say, okay, the cities should be visited in this order. So this is at the end what we are expecting from the quantum annealer. It will say us which variables are set to 1, which variables are set to 0, and from this we will deduce back the solution. But we are not over, because right now we are not making any minimization for the costs. This will only give us the closed roots. So we also need the cost. And let's also check the cost objective function. And this is what we want to minimize. So this xui, xvi plus 1, if they are both equal to 1, this means u is visited at time I, and v is visited at time I plus 1. So they are both 1. And we have the cost associated with edge uv. So overall, this objective function will give us the total root, total cost of the root. And we want to find the one with the minimum objective, with the minimum cost. So this is what we want to minimize, and we have some constraints. And this is what we end up with. Remember the penalty method. So we subtract 1 there, here and add a square. And we have a summation, because this is true for all cities v. Remember, v was fixed here, but this will be true for all v's. And we have an associated penalty here. And similarly, for this constraint, again, we use the penalty method. We subtract -1, square it, and we take a summation over the vertices. Sorry, I think this is a typo. It should be I. We take a summation over I, because this is true for each time step I. And here we have the cost of the root. And also we go to, this is exactly like here. So for each time step I, we check all possible UV combinations. And this is our final Cuba formulation. This is what we would like to minimize. Now, finally, let's move on to the traveling salesman problem with time windows. Here, besides trying to find the route with the minimum cost, we also have some time windows to obey, meaning that for each city, we have an early start time and we have a later start time. You may think this problem as there is a vehicle, and this vehicle is visiting the city, is giving some service, and this service should be given between the early start time and the latest start time. And if the vehicle arrives earlier, then it needs to wait. I will give an example of a non-feasible solution. Say initially we are at node 0, and then we move to node 3, and the cost of moving to node 3 is 2. So this means that we arrive at node 3 at time 2. Now let's check node 3. Its early start time is 4, but we arrived at 2. Therefore, we need to wait for 2 units of time, because we cannot give a service earlier than 4, which means that we will leave this city at time 4. And then from the city, we are moving to node 1 here. And the cost here is 1. And this means we arrive this node at time 5. But now let's check node 1. Its latest start time is 4, but we arrived there at 5. Therefore, this solution is not feasible, because we couldn't arrive to node 1 within its time window. So therefore, we would like to both minimize the cost, and also it has to obey the time window constraints. So there is one more layer right now. For instance, this route has cost 5, but it's not feasible. So it cannot be the solution. But if you check this one, you will see that it's obeying all the time window constraints. And you would like to find the one obeying the time window constraints with the minimum cost. Now, this is how the overall structure of the Cuba formulation for TSP-TW looks like. You have the root constraint, you have the time window constraint, and you have the cost of the tour. So this two was also present in TSP, but this time window constraint, it is something new. I will mention 3 different formulations, but actually I will go into details of only the first formulation. And those formulations are different in the sense that how we define the main binary variable for the problem. And based on this, they have different number of variable requirements. Now, let's start with the first one. I will call this Edgebased formulation. Here, please note that how we define the variables is different than how we did them for TSP. In TSP, it was that at time I, we are at city V. So it was node-based. Here, it is edge-based in the sense that we are visiting nodes U and V, so meaning that we are passing through edge UV at time I, let's say. And by fixing the first and the last, so this is also true for TSP, but I didn't go into detail. This, you can fix the first city so that you have a city 0, and this is your origin, and you start from here and you come back to here. So you can save some variables using this fixation of the first city. Now, a Cuba formulation for this problem was already given by Propolis et al. In 2019, but there was a problem in their formulation. First, let me describe their formulation. This constraint you see makes sure that each edge is traversed only once. And you can understand this because here you have 1 minus, and there is a summation. You see from you have a fixed I, and it's going through all possible edges. And outside you have a summation going through for each I. So this makes sure that each edge is visited exactly once. And this one is for the first edge, and this one is for the last edge. Those are the boundary conditions. And then you have 2 more conditions. This makes sure that vehicle leaves each city exactly once. If you check this in detail, you will see that here you have, you fix U, and you need to make sure that at least one of the variables XUV for any I is set to 1. So you leave city U exactly once. And similarly, you want to make sure that you enter V exactly once. So you fix V here and you try all possible UVs and I combinations. But then what is the problem? This seems like a reasonable formulation. What is the problem? The problem is what is called the subtour. In this formulation, we are not checking if once we leave city U, then the next city we go to, like, say you first traverse edge UV at time I, we are not guaranteeing that we will move from V at time I plus 1. And this results in, so let's say 0, 1 is selected for I equals 1, 1, 2 is selected for I equals 2, but it may be the case that 3, 4 is selected for I equals 3. And here, each city is visited, each city is entered exactly once, and each city is left exactly once. But still, we cannot omit the subtour, meaning that we cannot have a single closed tour. So therefore, we fix this formulation in the following way. Those two are the same. So we are saying again, each edge should be visited exactly once, and you should leave each city exactly once. But then we are saying, if you enter V at time I, then you should leave V at time I plus 1. So that we make sure that if UV is visited at time point I, then for some W, VW is visited at time I plus 1. And this makes sure that no subtours exist in the formulation. And this is overall how the root constraint looks like in this case. And now we can move on to time windows constraints. And for time windows, I will denote earliest and latest start times by EV and LV. And we will need an additional integer variable called omega I. And this will be the waiting time for the city at position I. It's not the ith city, but it's the city visited at ith time step. And for clarity, I will define something called arrival time. This is not an integer variable, but I will use just this notation to make things more clear. Here is a recurrence relation for the arrival time. And this is saying arrival time to the city I is equal to arrival time to the city visited at time I minus 1 plus waiting time for the city visited at time I minus 1 plus the cost of moving between edge UV, which is visited at time I. So this makes sense. At time I am at some city U, and now I am moving to V. If this is 1, then I will take here CUV. And if I arrived at city U at time I minus 1, and I waited there for omega I minus 1, and now I also have the cost. So it's the recurrence relation. And from this, we come up with this open form. So on the left, you see the A1, which is the arrival time to the first city. And it's basically so we don't have any waiting time, we don't have any previous city. So arrival time to the first city is only the cost of moving to that city. And if the variable x0 v1 is set to 1, meaning that v is the first visited city, then this arrival time will be the cost of moving from city 0 to city v. And for the arrival time now, if you open up this recursive relation, you end up with the following, which means the following. This summation here is the total waiting time until and including node at position I minus 1. And here, this is the cost of all the edges traveled until and including node at position I. And this also makes sense. So you have all the costs, plus you have the waiting time until you have the summation of all the waiting times until you reach city I. Now, why did we define this arrival time? Because it is important that the arrival time is within the time windows. And this formulation requires n cubed plus n delta variables. N cubed comes from xuvi, because for each edge, so you might have n squared edges, assuming the graph is complete. And you also have n time points. This is where n cubed comes from. Plus we have this waiting time variables, and those waiting time variables are, remember, integer variables, but you convert them into binary, and the upper bound for them is delta, and this is determined by your problem instance it's related to your latest start time. And now, having defined this arrival time and also waiting time, what we can say is, we call this service time, arrival time plus waiting time. And this should be greater than or equal to the early start time. So if we reach some city, then we might be maybe early and we might want to wait. But for sure, this should be greater than or equal to early start time. Or if you don't arrive early, then maybe you don't wait. And in case still your arrival time is greater than or equal to the early start time. But note that this formulation also allows that even if you don't reach some city early, you might still wait there. And you might move the waiting times between cities. Maybe you would need to wait in the following city, but instead you prefer to wait in the previous city. This is also possible. So this formulation is also allowing this. And this is not a bad thing because this is increasing the number of feasible solutions. You can assign more than one waiting time. And still you have a feasible solution. So the same route exists in the sort space with more than one possible assignment to the waiting times lesson. And this arrival time also needs to be less than or equal to the latest starting time of the corresponding city. And how do we know the corresponding? Here, this is AI, meaning that arrival to the city I. And this is the city visited, edge visited at time step I, XUV I. And here we take LV. And similarly, here it was XUV I, and we were taking early start time of city V. And this is how we find the latest start time or early start time of city visited at ith position. Note that only one of those variables should be set to 1 because we had such a constraint. Now, this might look scary, but this is how we make the conversion from the inequalities to the penalty methods. So this is the first constraint, and this is how it looks like in the Cuba formulation using the penalty method. We convert this into equality using the slack variable xi. It's the one here. But furthermore, we convert it into integer variables because those slack variables are originally integer and we need them to be in binary. And this is what this E stands for. It's the encoding. 0 is the lower bound, and this term here is the possible upper bound for the slack variable. And this one, again, since omega is an integer variable, we convert it into a binary variable. This is what this stands for. And we do this for all the constraints you see here. This one is converted into this one, again, using slack variable. This one is converted into this one into this one, and so on. So this is our term in the Cuba formulation, which is responsible for the time windows constraint. And here below, by the way, those AIs, remember I told you that they are not variables. You should replace those AIs by this term here. So your overall Cuba formulation is defined through X variables and omega variables only. And this is the cost of the root. It's easier. Here, you only have a summation through all edges, through all time points, and for those are the boundary cases. And overall, this is what your how your final Cuba formulation looks like. You have the root, you have the time windows, and you have the cost of the root. You might wonder why we didn't use the node-based formulation as in TSP, because this looked much more simpler. At least to implement the root constraint, it was much more simpler. So this is root. We can indeed use this, and now I will show you what happens when we use the node-based formulation. Again, we have a root constraint part, and this is exactly the same as in TSP. And this is also exactly the same as in TSP, the cost of the root. But now what about the time windows? And so this is a time windows formulation term for when we used edge-based formulation. And you can come up with time windows formulation for the node-based formulation by taking those xi uv variables and replacing them by xui minus 1 and xvi. Because if edge uv is traversed at time I, this means in the node-based formulation, at time I minus 1, you are at edge node u, and at time I, you are at node v. But then, okay, what is the problem? The problem is that here, if you check this, so this is already a quadratic term, And this is also getting squared, meaning that you will end up with something which is not quadratic. This is called a higher order binary optimization problem, or HOBO in short. And to obtain the Cuba model, you would again need a process called quadratization. And therefore, it will not give you anything. I mean anything in the sense that minimizing the number of variables. Overall, this is efficient, this HOBO formulation, because it is requiring only ON squared plus N delta variables, N squared coming from XVI's and N delta coming from omega again, but it's not a Cuba. So you cannot directly use this in quantum annealing. And this is why we preferred edge-based formulation. And finally, I mentioned another formulation, which we called ILP formulation. So in a work published by Karakoç and Altıparmak Dengiz, they have an integer linear program formulation for TSP-TW, and this is how they define their binary variables. XUV is equal to 1 if EdgeUV appears in the tour and 0 otherwise. And they also have some other integer variables like service time and waiting time. And they also had arrival time. The thing is, in the case of the integer linear program, it's not a really big deal to minimize the number of variables. They don't they don't need this actually. So what we did was we took their integer linear program. We removed some of the constraints which were not essential, in the sense that they needed those constraints to reduce the feasible space, because this is something important when solving integer linear programs. But our aim was to minimize the number of variables. And after removing some of the constraints, we ended up with this integer linear program with those two integer variables and those binary variables, overall requiring this many variables, which is, as you can see, more efficient than the edge-based formulation, assuming that latest start times will not grow so fast. And we converted this into Cuba formulation using the method I described at the beginning of the presentation. Here's a comparison for the number of variables. So we use the real data set for TSP-TW with increasing number of cities. Here you can see how the number of logical variables required increases. So you can see you may need up to 1 million variables for a instance with 150 cities. And at the beginning, Edgebased seems like competing with ILP, but as the number of cities grow, you can see that ILP has less number of variable requirements compared to Edgebased. Node-based is not Cuba, therefore it's not really fair to compare them together. And another thing is on the real machine is embedding problem. The D-Waves quantum hardware, in that hardware, not all the qubits are connected to each other. So remember at the beginning when I mentioned Ising model, I said you need to apply those JIJs between qubits I and j. But in D-Wave machine, not all qubits I and j are connected. So what you do is, for a single logical variable, you define multiple physical variables, but they all represent the same logical variable. And this process is called embedding. And the same variables representing, and the variables representing the same logical variable is called a chain. And this increases the number of physical qubit requirements heavily. And in this graph, you can see this. We generated 10 random instances with 3, 4, and 5 cities. And in this graph, you can see that for 100 logical variables in the edge-based formulation, you need around 1,000 physical variables. And this is really quite high. I see that Karim has a question.
Yes, maybe we can interrupt. Karim,
yes.
Would you like to ask your question?
Yeah, thank you. Thank you so much for this opportunity. And thank you also for the great presentation. I would like to ask about the embedding. Which COPO did you use, the higher order Hamiltonians or the basic binary Hamiltonian?
Those graphs are for Cuba formulations for the Edgebase and ILP. And we use the default algorithm by DBase. So we did not implement any special algorithm for the embedding. It's their default algorithm.
Okay, what I meant by the, it's not like the a special implementation for the embedding, but for example, like the Edgebased, is it the higher order Hamiltonian or the HOPO, or is it the COPO itself?
No, it's not HOPO. It's not HOPO.
It's not HOPO. Okay.
No.
Okay. Thank you so much. Thank you.
It's HOPO. So this embedding problem is itself an NP hard problem to find the most efficient embedding. And this is something, so these chains are problematic if you have really long chains. This is also something problematic. You need to set a chain strength. It's another parameter in your problem. So this is something which makes annealing process a bit harder. But you need to face this because this is the topology of D-Wave's advantage hardware. And you see which qubits are connected to each other. So not all qubits are connected, as you can see. And another thing is the selection of the penalty parameters. And for that, so for root, we use a single, for the root constraint, we use a single penalty. And for the time windows, we used another penalty. So we had to set two different penalty values, P1 and P2. And we tried some kind of grid search, and we used simulated annealing, which is a classical optimization algorithm. So this experiment part was just to see like what's coming out. So it was not the real purpose of the paper. Our real purpose was the formulation, but we also wanted to see what's coming out. So it was not like to show any advantage or something like this. So we used simulated annealing to find out the best penalties where we could find the most probable solutions, more optimal solutions. And using this and our instances with 3, 4, and 5 cities, we run them on D-Wave quantum annealer. The results were not really promising, actually. Here on so those graphs are histogram. As the result of the annealing process, you get 1,000 samples. Like you can set the number of samples, but in our case, it was 1,000. And this histogram shows you the energies of those samples. And this red line is the real lowest energy, which we computed ourselves. For 3 cities, okay, it was good, but 3 is really a small number. And like for 5 cities in the Edgebase, we couldn't get any feasible or optimal solution. In the ILP formulation, we could get some feasible solutions, but they were not optimal. And here also, like the first row is Edgebase, second row is ILP, and 3, 4, and 5 cities. And you see the ratio of feasible and optimal solutions among the 1,000 solutions. So based on those experimental results, what I can conclude is during, also according to my experience with this problem, the choice of penalty values, this is something which is not easy, first of all, if you have multiple of them, like in our case. One could try some other approaches like KOA, because then you could also directly use HOBO representation, higher order representation. And I can also say that for larger instances, hybrid solvers can be a better alternative. And we had a recent paper, a preprint, it's available on arXiv. We checked out this new constraint solver of D-Wave. And we solved a problem called vehicle optimization problem using this new hybrid solver. And the results seemed more promising, at least comparable to classical solvers. It was a real data set. And the results were not bad. So I would say that, especially for constraint problems, that solver might be a better alternative overall. And this is the end of my presentation. I will be happy to answer if you have any questions.
All right, great. Thank you very much. Very nice, very clear presentation. And it's a very good introduction, not only to solving traveling salesman problem, but in general, combinatorial optimization problems. So yeah, there is a question from Karim and from Akash. So Akash, maybe you can ask first this time.
Yeah, sure. Thank you. Özlem, I have two questions actually. The first question is regarding a correlation. So far, it seems like the node-based formulation uses less number of variables, right? If I'm not wrong, n square plus n delta variables.
Yeah.
My question is whether the process of correlation computationally expensive, and why wasn't pursued? What is the limitation with that?
In that case, quadratization ends up you with again n cubed variables, and it was again really identical to the edge-based formulation. This is why we did not consider it. So think about this formulation here. What you would do here is to create a new variable to represent this product, but this is again edge-based. The only part that is different will be the root constraint, but for quadratization you need some additional constraints, and this will also like introduce some additional hardness, because now you also have those additional constraints which you will incorporate into your objective function. So this is why we didn't. So since it was not providing any advantage in the number of variables, we did not try quadratizing it.
Right. Okay. Thank you. And coming to the second question, it's regarding the comparison between simulated annealing and quantum annealing, right? In quantum annealing, you said the number of raids was for 1,000. How many number of raids did you run for simulated annealing, since it is machine dependent? And how much time did it take in comparison to quantum annealing for the same problem cases?
So actually, we didn't compare the performance of simulated annealer and quantum annealer, but we used simulated annealer only to find out the best penalty values. But I can say that simulated annealer was able to find the optimal solution for all of the instances, while quantum annealer could not find. For quantum annealer, the annealing time was 50 nanoseconds, as far as I remember. For simulated annealer, for sure, it took longer time. But in our case, we didn't do benchmarking with simulated annealer. We just used it for finding out the penalty parameters.
Okay, got it. Thank you very much.
Thank you.
Great, thank you. There was a question from Karim regarding the hardware limitations. I believe that was a question about probably related to this ratio of feasible and not feasible solutions. Karim, if you are interested, you can unmute yourself once again and just specify.
Yeah, thank you so much. Yes, exactly. In this slide, so you're saying that for 5 cities, we couldn't get any good results regarding the edge-based method. Is it because of the hardware itself or the formulation itself?
If you compare the number of variables needed by 2 methods for 5 cities, for instance, here you see that the Edgebased is requiring maybe I think there is a problem in the there's a problem here. Edgebase is requiring much more. Maybe I have a problem in the graph. Yes, this should be Edgebase and this should be ILP. Sorry for this. So Edgebase is requiring much more physical variables and logical variables compared to the ILP. I think this is one of the reasons, because this also results in increased chain lengths on the machine. And setting this chain length is also another problem, because if you increase it too much, it overrides your optimization. If you decrease, you end up with broken chains. So we tried some different chain lengths to see which ones were working better. I think it is also related to the hardware, because we realized this pattern in all of the samples. So this is the ground state energy, but the lowest sample starts from here. And this happened in many of the instances. It was not able to reach it was not able to sample from the lowest energy solutions. We tried different annealing times, but it didn't help much. I'm not sure.
It's a hardware problem in its essence.
I believe this is the case. I don't know, like there are some additional parameters which did not try, like annealing schedule. We did not try changing those values. And also, so it might be also dependent on the problem, because in quantum annealing, annealing time is dependent on the gap between the ground state energy and the first excited state. And maybe with this formulation, maybe this was too small, and this means that we need too long annealing time, which is not possible. So it might also depend, or it's not also depend on the problem. Because the promise of quantum annealing, it also depends on the problem and the instance size. Yeah. So this might also be a problem.
Okay, thank you. Thank you for these insights.
Great.
Thank you.
Yeah, there is a question from Livan. The question is how many cities for 5,000 qubits, I guess. So I believe that the question is, so how large instances of the TSP, let's say TSP, we can solve with 5,000 qubits that we probably currently have on D-Waves machines. So I believe that we can try to read it from the plots.
I mean, for TSP-TW, so because of the embedding, this limits your number of variables too much. Actually, I tried this, but right now I don't remember. But so right now, checking the increase in the number of variables, I will say, but okay, let me tell you something. In our paper, in the appendix, we have a table based on real data set, and there you can see different number of cities and the corresponding number of variables. I think it might be better if you can check this. There you might see a better idea about how large instances can fit to D-Wave.
Okay, good. There was also a question about the paper with the details. So I know that you published a paper with exactly the same title as the presentation today. So I've just shared the link. So if anyone is interested, feel free to just check out the article. It's available publicly on Archive. I've also just shared a link to our YouTube channel where we are going to just publish our recording. Regarding the slides, Özlem, would you like to share the slides as well?
Yeah, sure.
Yeah, so the slides will be also available. So we'll just try to distribute the slides. And there's also a question from Marco. Marco has raised his hand. So Marco, you can unmute yourself and ask.
Thank you. So I hope you did not already answer that because my connection had issues, but I have two questions actually. The first one is so it's a good introduction actually to quantum annealing, and I would like to know, is there a complexity study of quantum annealing telling you that, for instance, if you want to solve that problem with a classical computer, you will need an exponential number of operations as you have is there a complexity analysis of quantum annealing that tells you, for instance, that you can solve that in polynomial operation? And if so, how is defined an operation in quantum annealing? Because it's kind of an analog process and it's different from gate-based quantum computing.
Thank you for the question. So the thing I mentioned about this energy gap, this is related to annealing time. And I think this is what is considered when people think about advantage that quantum annealing could bring. So if this, when you consider this minimum energy gap, if T is growing like an exponential, then you could say, okay, this is not bringing advantage for this problem. I think this is other than that, I don't know any other complexity analysis. But there are some papers exploring for which problems could you get an advantage, or there are some also works about some random instances and whether annealing is providing any advantage or not. But as far as I know, it's not like the usual way of complex analysis thing we have.
Okay, so it's related to the energy gap you have in the. Okay.
Yes.
And I have another question. Like, what are the experimentally with quantum annealing? I know that it is somehow less sensitive to noise than gate-based quantum computing. I've read stuff like this. So, what are the main challenges of being able to implement this on large problems? So this, I guess you probably said, but as I said, my connection dropped several times. So,
so as far as I know, also noise starts to affect if you have too large annealing time, and for some problems you need a larger annealing time. So this is a challenge because you need to increase the annealing time, but it will introduce noise. The other thing I mentioned was about chain lengths, and this is related to the embedding problem. So say you need to interact both x1, x2, x2, x3, and x3, x1. So forming like a triangle, but you don't have such a structure on the real machine. And you need this embedding problem resulting in long chains. For instance, D-Wave is giving some warning if you have chains longer than 7 qubits, meaning that 7 qubits representing a single variable. But often this is the case if you have a complicated problem. So also, I think this depends on the type of the problem and the interactions within the problem. The current topology might be better working for some problems, which can be better embeddable into the machine, maybe. And as I said, we use the default embedder of D-Wave. Maybe some better ways for embedding exist. We didn't try this.
Okay, thank you.
Great.
Thank you.
Thank you. There's also a question from Achari. So yeah, you can unmute yourself.
Hello, can you hear me?
Yes, yes.
Yes, hello.
Is there another possibility to do quantum annealing without D-Wave? Or how can we adapt quantum annealing algorithms to other usual quantum devices that are not like using the technology as D-Wave?
So I can say two things. There is something called digital anneal, which is a classical machine inspired by quantum annealing. It's offered by Fujitsu. It's something new, I suppose. And so this is like an alternative to quantum annealing in the classical setup. And if you think about gate-based computation, you could view QAOA algorithm as kind of quantum annealing adapted to the quantum gate-based setup. So I think you could consider that. And there is also something called simulated quantum annealing, in which you use classical techniques to simulate quantum annealing.
Okay, great.
Thank you.
Thank you for the question.
All right, do we have any more questions? I don't see more questions on our chat. There's a question from Akash. What sampler was used with regard to quantum annealing? Was it D-Wave sampler or I guess that it should be solver. Was it D-Wave solver or a hybrid solver?
It was D-Wave advantage solver, so it was not hybrid.
Okay, so it was only quantum solver.
Yeah, it was only quantum solver.
Right. So, Özlem, my question was regarding the kind of sampler you used. So, in case of DBA sampler, right, you have to do the entire embedding thing by yourself. But in case of leap hybrid VQM solver or leap hybrid CQM solver, the ocean SDK tries to do the decomposition and the embedding for us, right? So, is there any comparison between this D-Wave sampler and hybrid sampler, and was there any improvement in result by this hybrid samplers provided by Ocean SDK?
I didn't really get the question, but if you are asking whether we compared hybrid solver versus D-Wave solver, like for curiosity, I ran some instances on the hybrid solver, and it was able to solve. But we didn't include those in the paper, so I just tried some of the instances. But we mainly focused on the pure quantum solver, D-Wave Advantage solver. And it's on embedder. We didn't tune anything about embedding.
Okay, got it. Thank you.
Okay, great. Do we have any more questions? I don't see more questions on our chat. I can see that Achari still hand raised, but I believe that the question has been already asked. Or Achari, do you have more questions maybe? Probably no. Okay, thanks. All right, so I think that was all. So Özlem, thank you very much once again for a great presentation and also answering all our questions. We had quite interesting discussion today, and I believe that we learned a lot. So yeah, as I said,
very much again for the invitation.
Okay. Great. So before we finish, I would also like to invite you to our next meeting. So let me maybe just share my screen once again for a while. Yes, so first of all, I would like to thank our strategic partners for supporting us, Naruto and Kogit, and for our to our honorary partners for helping us organize this event. And I would like to invite you to join our next meeting. So in fact, our next speaker will be from D-Wave. So you'll have opportunity to just ask some even more detailed questions regarding D-Wave's quantum annealer and maybe also some quantum annealing approaches. So the event will be on 9th of May, and the title is Building Hybrid Applications with D-Wave. So I already invite you to join. And if you are interested, of course, let's stay in touch. You can just join our Facebook group and follow our profiles, follow our YouTube channel. So the video recording will be available on our YouTube channel. You can join our mailing list to stay up to date as well. And that's all for today. So thank you. Thanks to all of you. Once again, I will now stop sharing my slides and also stop recording.